Good evening. Hello, everyone. Thank you so much for coming. Welcome to the Allen Lecture in Structural Design. My name is Caitlin Mueller. I'm a faculty member here at MIT in the Department of Architecture. I'll start first with our land acknowledgement. MIT acknowledges Indigenous peoples as the traditional stewards of the land and the enduring relationship that exists between them and their traditional territories. The land on which we sit is the traditional unceded territory of the Wampanoag Nation. We acknowledge the painful history of genocide and forced occupation of their territory, and we honor and respect the many diverse Indigenous people connected to this land on which we gather from time immemorial. And now it is my pleasure to introduce the Edward and Mary Allen Lecture in Structural Design. This is the 13th of these lectures that we've had starting in 2012. This endowed lecture brings a distinguished structural designer to MIT each year to share work in a public lecture that's here tonight and to work with students in a design and setting. The inaugural Allen Lecture was delivered in 2012 by the celebrated German structural engineer Jörg Schleich. Over the past 12 years, we have been fortunate to host some of the most inspiring and creative designers from around the world here at MIT, including Bill Baker, Sigrid Adriansens, Guy Nordenson, Kate Siminen, Jörg Konzett, Janet Eckelman, and many more. Ed Allen was a member of the faculties of Yale University and the Massachusetts Institute of Technology, and frequently taught as a guest at other institutions around the world over the past over 30 years. He is the best-selling author of numerous important books, including Fundamentals of Building Construction, The Architect's Studio Companion, and as you all know well, Form and Forces, along with many others. For his inspired writings and teachings, Ed was the recipient of the 2005 Topaz Medallion for Excellence in Architectural Education, awarded by the American Institute of Architects and the Association of Collegiate Schools of Architecture for lifetime contributions to architectural education. Sadly, Edward Allen passed away in July of 2020. However, his love of learning and enthusiasm for building and design will continue with this generous gift to MIT to support activities and teaching that will improve the ability of architects and engineers to design efficient, economical, and expressive structures. Professor Mary Allen is also a distinguished educator and scholar, having taught biology at Wellesley College for more than 30 years, where she is particularly noted for mentoring undergraduates in research. She was awarded the Wellesley College Pinansky Prize for Excellence in Teaching in 1986 and the American Society of Microbiology Karski Foundation Distinguished Teaching Award in 1995. Mary Allen is here with us tonight. Please join me in thanking her for making this very special event possible. Thank you, Mary. And now it is my pleasure to introduce our esteemed department head, Professor Nicolas Demanchot, who has a special announcement.
Thanks, Kevin. Yeah, esteemed is arguable, but I'm very happy to be with you here tonight. I wanted to take this moment to unofficially announce something that I really felt like was very important to bring into the conversation tonight. I was not fortunate enough to know Ed Allen in person, although I do own all of his books, and did so long before I came to the Department of Architecture here at MIT. But it is an enormous pleasure, along with the books, to see the many other really beautiful ripples that flow out of his career, love of structures, and no doubt something very interesting to say about the mathematics of the ripples themselves across the surface of architectural education. So this is not the official announcement, but I have been cleared on behalf of the Eli and Roger Goldstein and their mother Roseanne. Eli and Roger were both students of Ed's here at MIT. To announce the S. James Goldstein's 46, 48, BARC 49 and Family Fund, which is a new donation here to the Department of Architecture, very much in the intent and memory of the focus on sustainability and building and construction here in the department that was so important to Ed. that I'm just really delighted to say will allow us to expand our climate studio program, which has been a really important urgent innovation in the department to meet the urgent need to address the relationship between climate, carbon, and building that we'll hear about tonight, from 1 climate studio to 3 parallel climate studios in the department, which will just really be an enormous gift to our faculty and our students, and the focus on engineering, construction, and sustainability that was so important to Ed at the moment. I would argue that the world most needs that focus. So with enormous thanks to the Goldstein family, who unfortunately cannot be here tonight, but particularly because of their regard and esteem for Ed, very much wanted me to share this news with you tonight. I want to extend the department's gratitude, and of course our gratitude to Mary and the memory of Ed, whose influence lives on in this and many, many other important edifices of the department's own structure. So thank you very much, and let me now hand over to my definitively esteemed colleague, John Ochsendorf, to introduce tonight's speaker.
Thank you, Nicholas. That's an even more debatable use of the word esteemed. But our speaker tonight is truly esteemed. And this, for me, feels like a full circle moment. You know, when I first got to MIT, one of the things I had the honor of doing was working with the Goldstein family on the Goldstein Lecture, and Ed would always come. And I think the Goldstein Lecture also partly inspired Ed and Mary to endow the Allen Lecture series. So it really feels like a full circle moment. And but let me get down to business. You're all here to hear from our invited guest, Professor Philippe Block, who's a professor at the ETH in Zurich, who heads the Institute of Technology and Architecture at ETH, but also directs the Swiss National Center of Competence and Research on Digital Fabrication. And for anyone who has visited the NCCR at ETH, it's a spectacularly understated Swiss competence in research, because I think we can say true excellence in research. It's unlike almost any facility anywhere in the world. Philippe has the privilege of directing it. And of course, he's well known to us because after he earned his undergraduate and master's at the VUB in Brussels, where he studied both engineering and architecture, he came to MIT and earned the SMArchS degree in computation. Some of us in the room remember Philippe from that time. And then during his computation, he became enamored with this historical material of stacked masonry blocks and how they might stand up. And he continued on for his PhD in building technology, where I had the great privilege of working and learning from him. If we think about Philippe's impact, he's of course known internationally for his design work. He's won a whole slew of awards. Importantly for me, he serves on the board of Wholesome, and he chairs the Health, Safety, and Sustainability Committee, which has major global impact with on the cement side of the industry. But the impact of his students is perhaps even greater. So if we look at members from his group, the Block Research Group that he co-directs with Tom von Mele at ETH, members of his group are now professors from the University of Washington and Washington State, Cal Berkeley in California, Massachusetts, at BU, and at MIT, we have a new professor who recently completed a PhD and will be hired in between BT Computation and the College of Computing starting next year. So that's very exciting. In Pennsylvania, he has the state locked up with a professor at UPenn and at CMU. So by my count, if this were the Electoral College, I think you're at 100 votes across those states with only a few more to go to seal it. And but for me, really the significant thing and why Philippe is so important to have here for us is because his dissertation and his work helped to rejuvenate and re-energize graphic statics as a design technique, which was so near and dear to Ed's heart. And Ed taught graphic statics to both me and Philippe, and it was really developed at ETH in the 19th century. Philippe reintroduced it to ETH. So the same methods that were used to design the Eiffel Tower that came from ETH were reignited here at MIT and back at ETH. So it just feels like an amazing dialogue back and forth. And I still believe, as I said 19 years ago at his SMArchS thesis presentation, that the fact that he works on equilibrium of rigid block systems means he has the most prophetic name in history. Please join me in welcoming Professor Philippe Block back to MIT to deliver the 13th Ed and Mary Allen Lecture. Thank you.
Thanks, John. Yeah, for this one I'm a bit nervous. It's nice to be back. It's particularly nice to be back for such an important lecture. I spent the weekend before this in New Hampshire, where there is, John took me, my wife, and our small daughter there to basically discover Ed's passion, his quirky details, his discovery, his inventions in structural design. So I was spending the weekend basically looking at all these amazing discoveries, many of them indeed understated. Basically, the house was 3D printed in the 70s, so quite special to be in such a location. Again, well done by John to kind of put me already in the right mindset. We also talked a lot over the weekend on exactly how Ed came into my career, but I guess this talking now, John already covered it all. Indeed, I would absolutely everything I've done and what I keep doing actually started from, and this is not an overstatement, this is really a true fact, from actually discovering the strength of the relation between form and forces, and how that really can change design. And that is something, there's many people that have done graphic statics historically and present, but the one single person that actually showed the power of graphic statics and design was really Ed. And so that is indeed what we learned from Ed, and that is what triggered, it was the seed for my PhD. It is still what we do in our research, so you will see this in what I present, that equilibrium is present everywhere, and how we discover equilibrium is through graphic statics. And then lastly, actually, indeed, very proud to bring back graphic statics to ETH after it having been forgotten for almost a century. And so my teaching is entirely graphic statics based. And so I can proudly say that I'm required to teach in German, and I have not done so for 15 years. I teach in English. But because I teach in graphic statics, I think that my 300 to 400 students per year, that no one has ever complained or filed a complaint that I teach in a language that I'm not supposed to teach. I think it's because of the power of graphic statics, the power of geometry. So with that, it really is a true honor to be here in this context. And let's see what equilibrium can do, and at least it still drives me every day, and I'm excited to share my story and where we're at right now with equilibrium. And indeed, John, I still do blocks, so I'm very proud of my name. It's a good one. Let's get going. So a bit of a bold statement, rethinking construction, but it's clear that if you hear that my most important kind of backing was by working with John, that shaped really what I'm doing now, then it's clear that I will be looking at the past and learning from all the amazing things that the master builders could do to hopefully design better in the future indeed. I guess this audience, I'm preaching to the choir, I hope. Our industry has really a tremendous impact. Here I'm focusing on the negative one. These are rounded up or down global numbers of the impact of our industry, building and construction on greenhouse gas emissions, on so man-made greenhouse gas emissions, resource consumption, waste production, and energy. Today I will be talking about the blue part. We can discuss about what percentages the distribution is. So there's two key contributors to these emissions, the operational emissions and the embodied emissions. So the embodied emissions are the ones that have something to do with materials, with building, and operations says it, right? That is once we start to turn the key and use the building. one of the reasons that I'm excited to be a structural designer is that in a cheeky way, I could make a bit of a shortcut here and say that if we have the the political will and we all use green sources of energy, then we have operational emissions check, right? That is not the case for embodied emissions. So there is no silver lining. We really have to kind of rethink fundamentally how we do things. This will be the only equation, so because I'm also part engineer, so one equation seems appropriate here at MIT. The only equation I will use. You see again some usual suspects appear. John Ochsendorf, very early work with Catherine de Wolf, my colleague at ETH as well, also an MIT alum. I like this equation because it's simple and it really very clearly shows the three main levers that we can use to reduce the global warming potential of a construction. Again, I'm talking about the embodied emissions. So what you see here is MQ, material quantities, right? Then we see ECC, embodied carbon coefficients. So you can, per material, per where you use this material, you can calculate what the impact of that material is. And then T stands for lifespan, surface life, so that has something to do with time. So what's clear is that we want to reduce the amount of material that we use then. To reduce the global warming potential, we want to use better materials with lesser impact. But we also want to actually rethink what is the lifespan of a resource, be it a material, a component, or a building. And I insist on standing here because I think sustainability is too often unnuanced and simplified. And you hear all the time, wood is good, concrete is bad, for example. But here you see that it's a bit more intricate. You have to start to make compromises between these three parts. So the first one again is clear, less material, better material, and then can we find ways to extend the lifespan of our resources? So our group has been looking at this with these three approaches. The first one, strength through geometry. This will be very clear what I'm talking about there. Second one, material effectiveness. As you see, I'm not using the word efficiency because it's not just about lighter, for example, but it's about using the material how it wants to be used. And then I will show you how we wrap it all together and we can extend lifetime by really being very precise about circular construction. So the first one, strength through geometry. There, another quick wink to my advisor and eternal mentor, John Ochsendorf, these beautiful fan vaults at King's College. They are spanning 13 meters with simple stone that is standing still after more than 500 years because they have the right geometry. And these stones are, the continuous bit is roughly 10 centimeters, so a few inches thick. So if you calculate the thickness or thinness of such a shell, then this is proportionally equivalent to an eggshell. So this, to me, when I started at MIT, there was a little bit of a resistance that I would be working on old structures. But the more I was working on them, the more I realized that we might have really forgotten quite a bit in modern design and engineering. So how do you even find the geometries of these structures? How do you know how safe they are? And so this was the starting point of my PhD indeed. And again, considering that we activate such humble materials in such a robust way for with these kind of thinness, that became not just a fascination, but also a starting point to do things better. So in the beginning at ETH, we took my PhD to develop tools to share this kind of, this richness of discovering equilibrium in compression. And so here, these are three-dimensional versions of graphic statics where you can really, in a very explicit way, understanding the relation between compression shells on the top and the forces in them. We shared these tools very early on in tools like RhinoVault, so that this knowledge would not just be stuck with us, but everyone could start to explore. But you can do whatever you want on the computer. You can make a lot of fancy pictures. So we took the opportunity, the invitation of the 2016 Venice Biennale to clarify that this really works, that this is not just a fun toy to explore kind of things. What you're looking at here is, it's called the Armadillo Vault. These are 399 pieces of cut stone that are held together like the Gothic, old, beautiful masterpieces because of their geometry. So there is no mortar, there is no glue, there is no reinforcement. So these pieces of stone were dry assembled by expert masons from Texas, the Escobedo group. And this then resulted in this statement. We wanted to clarify that should we not bring back these elegant principles that make a cathedral still stand after centuries, not just an aesthetic statement, but really also a statement about efficiency and the beauty of achieving strength through geometry and not just through materials. Of course, I could give you an entire lecture on what we had to do to realize this project in just 5 months, all the way from the new design tools and engineering tools to the fabrication optimization. But I want to stick to the narrative and what I want to show you with an image like this. So again, remember, there's nothing holding these stones together, only gravity, only their geometry. So here we're talking about not even 2 inches of contact. And I hope this image speaks for itself, that if you get strength through geometry, you can significantly reduce mass force spanning space in efficient ways. I will piggyback on a project that I was very thankful to be part of, not from the beginning, but I could use my brand new concepts from my PhD to assess the safety of these vaults. You all know this project well, Mapungubwe Interpretive Center in South Africa, a project by Peter Rich, John Ochsendorf, and Michael Ramage. This project introduces tile vaulting, so a Mediterranean traditional technique that doesn't need any formwork, scaffolding to realize these structures. So you build in stable sections from the boundary conditions onwards. And so this technique was, of course, introduced in such a remote kind of context because resources are scarce, and it was really important to activate local resources, not just the local villagers, but also local materials. So this is beautiful Catalan vaulting, Guastavino vaulting, tile vaulting, timber vaulting at work. But what's special about this project is that it didn't use the typical fired bricks that are used in the traditional techniques, but instead unfired soil-pressed bricks with a little bit of cement to stabilize them. And so these bricks were basically built by the local villagers one year in advance. Why am I showing you this project? It's an older project, but it's still a project that when I see these 2 images next to each other, I'm still surprised that this works. So why am I showing you these 2 images? On the right, you see that the tiles are brought on site in very small packages because they are actually extremely weak. They're designed to just take a little bit in compression, 1 to 3 megapascals in compression. I actually don't know what that is in P. So it's basically peanuts in compression, 10 to 15 times less than a standard concrete in compression. But if you take one of those tiles, you can just break it in your hand. So this is not a material that you would consider intuitively as a structural material. And if you see on the left, by placing the bricks exactly where the forces flow in compression, you see that this is indeed a robust system. And in fact, that is how we used to build. In many basements, you see these kind of little vaults appear. No surprise, because we wanted to activate these humble materials. Quick teaching moment. An arch is a very good geometry for a certain loading case. If you don't have a lot of double curvature, like in the armadillo vault, then you need something to take the live loads, right? And so here you see the red line, by the way, represents where the forces want to flow to the supports in compression only. So another strategy than using double curvature is to add stiffeners so that you provide a possible load path in compression for these forces to find their way to the supports. And then if you add a tension tie, what I've just done with you here, why the tension tie? Because an arch pushes on its neighbors, and so you can absorb this horizontal thrust with a tension tie. What I've just done with you in the last 20 seconds is basically providing a 100% equivalent, structurally equivalent system than our reinforced concrete floor plates and beams, but one that uses 70% less material, right? So this is really not rocket science, this is just physics. And so this is quite dramatic, isn't it? Just by listening to the material and following where things go. So this is then a beautiful picture of Mapungubwe from the inside. The reason that I show you this project is to show another aspect of getting the geometry right. So if you get strength through geometry, then you not only can reduce the mass significantly, but because you align your material to where the forces go, you actually have very nice stress distributions, and so you reduce the stresses in the system. So stresses means, for those who don't understand these terms, it means that we can activate very low strength materials, as is clear here in this project. And that is important because there's almost a one-to-one relationship between how strong a material is asked to be and what its carbon footprint is, right? And so this is a second aspect why I care about activating strength through geometry, because we can reduce mass and reduce carbon at the same time. Okay, big jump to this project here. I will talk about it in detail later, but it looks a little bit unique. This project started in 2011 when I was almost fresh professor at ETH, and I thought building shells was what one wanted to do. So let's quickly look at the roof. So what we did there, and why I show you this, is it's another version of strength through geometry. There we actually use strength through geometry to make very efficient formworks rather than the structure itself. The reason for this is that structural geometry is non-standard geometry, it's curved geometry, and so we can design whatever we want. We want to be able to realize then these forms efficiently. So this is a beautiful shell in Lausanne at EPFL. This is how it was built. So maybe what you see here is that you need a lot of scaffolding. You need a full foundation to support all this scaffolding. And then you see this beautiful, super precise timber structure being built that will only last 28 days until the concrete is cured. And then it turns into this. Typically single-use material. So what you see on the left, all kinds of different ways to make this rigid formwork. And so what we wanted to do in this project was to use a flexible formwork where we then really understand how to basically stiffen that formwork because of its geometry again. So in this case, we go from compression only to tension only. So we developed this tensile formwork. We developed a kit of parts where all the cleverness is in the nodes, so that we could actually scale up this idea of flexible and fabric formworks to the scale of real construction. These nodes allowed us to know exactly where the formwork is, to develop algorithms to retighten and really control the entire flexible formwork. But also the node actually helped to reduce this crazy complexity of the global efficient shell to a local reference of every 40 to 60 centimeters. The regular worker had that reference, where to place the reinforcement, how thick the shell had to be, how to install the insulation, and so on. So this was a prototype. John talked about our facilities. So in this case, no robots were used, but we built this full-scale mock-up. And then we went on site with this building kit where the cable net, by the way, supports the wet concrete, and then the fabric allows you to apply the concrete on top. So this is not a beautiful concrete, unreinforced shell as what I will be talking about mainly, but we're still talking about only 5 centimeters and 3 centimeters. It's a double layer shell of a thin structure here. So a quick digression, but nonetheless, we managed to use strength through geometry to make a super lightweight, efficient formwork. And you know you're doing something right when an influencer visits your project and takes pictures. Another reason why I talk about this part of a project is because this was the first project that we did entirely using Compass. Compass is an open source computational framework for collaboration and research in the AEC industry. So it allowed us to really combine and introduce all these innovations into a real project. This is a permanent building. And so all the way from coupling the fabrication to the FE and so on, this is not that new, But what is new also is that we used it, as our engineering colleague called it, BIM on steroids, so building information modeling, to connect all these different partners, more than 40 subcontractors that had to come on site, many of which had absolutely no experience with computation or complexity. All right, let's get back on track. So the first one was strength through geometry. So I showed you that we can really address already the 2 of the 3 levers with strength through geometry. Let's talk about material effectiveness. So when I talk about concrete, and I will be talking about rethinking also construction in concrete, you typically think of this. But this is actually not concrete, this is reinforced concrete. And indeed, we have been using reinforced concrete because concrete is like stone, a material happy in compression, but not in tension, not in bending. And that's why we have to make this hybrid material. So concrete has been under a lot of scrutiny. It's the evil on this planet, as many state very, very clearly, like here, a big feature by The Guardian in 2019. But is it correct to just focus the material? I already gave you a hint in the beginning. It's not just about the material, but it's the combination between where you use the material, how you use it, how much, and then also the lifetime. You can use all kinds of charts, from the famous Ashby to the ICE, which is one of these databases that calculates embodied carbon coefficients here per unit mass. The LCA or sustainability experts in the room might say unit mass is not the correct metric. That's not my point. You can use any calculation. You will see that if you look at concrete itself, then it is not that bad of a material. In fact, it ranks much better than other typical materials we use, engineered timbers, steels, and so on. You see that steel is at least 10 times per unit mass higher on the embodied carbon coefficient. And by the way, I'm using 100% recycled steel because that is common practice, at least in Europe, for any reinforcement. So if you were to use virgin steel, then you are talking about factors of 30. The point here is that what about we start to look at concrete as the artificial stone that it is? And you probably see where I'm going with this. So if we listen to the material stone, artificial stone, then perhaps these beautiful geometries of the past are indeed the right geometries. So indeed, we already looked at this. We can not only reduce the mass globally by 70%, more precisely, instead of forcing a material to be in a geometry that it doesn't want to be, that flat floor plate or beam, but you reintroduce the natural arch, then you see that we, for free, get 70% reduction of concrete and 90% reduction of steel. So we thought, okay, instead of only having the simple arch with the stiffeners, can we do more? And we translated this in 3D. So what you're looking at here is a structural model that is a 3D vault that accumulates to corners. Then you see that the stiffeners that take any loading case in compression to the corners also accumulate to the corners. And then what you just need is a restraint of the corners that, for example, can be a tension tie. And that is also why I showed you that crazy project with a wild roof, because it was the first time that we could, in a permanent building, show this concept, not in our context, so in Switzerland. So the floors that you look at have an average span of 5 meters, so they span 5 meters. But if you look at the section, the structural thickness of these floors is 3 centimeters. So how much is that? Just over an inch? Yeah. So 1 inch thinness, unreinforced concrete, low strength concrete with more than 50% of recycled content. So look, by the way, also, maybe you've noticed this little dot there at the corner. So this little dot is actually drawn to scale. So we have a 12 millimeter steel kind of rod that holds it all together. So that is the only reinforcement bar. So of course, dramatically different than how we build our structures. You can go visit it. Everyone is very happy in there. There's no cracks. Everything works perfectly like the Gothic or any masonry system indeed. All right, why am I excited about this one project here? Well, we have some more challenges, not just the global impact, but also the next 20, 30 years will be many more people on this planet. people like Bill and Melinda Gates in their annual letter in 2019, but I believe others before, have calculated this to really clarify what the challenge is for our industry. In order to provide adequate housing and infrastructure for all these people still to be on this planet, we will be building the equivalent of one New York City every month for the next 40 years. That is really a daunting task, already considering that we have these very negative impacts. Another aspect is that we are densifying, we are building higher. This is not necessarily my vision of the future, but it is a reality that we have to address also the typology of medium high-rise construction. If you look at any of these buildings, so medium high-rise construction, so let's say roughly 10, 15 to 40 stories building, you see this image appear. So what am I showing here? These are basically the weights that are being considered in design of these structures. And you see that on average, 75% of the weight of that building is in the structure, right? So an absolutely mind-blowing or weird situation that the structure is mainly there to keep itself up, not us the users. To give you context, there are the 5% imposed loads, half of those are us, the users in the building, right? So absolutely mind-blowing and worrisome kind of news, particularly as a structural designer. If you then zoom in a bit more, then you see that more than half of that structural mass is in the floors. So another way to translate this New York City story there is that we will be building more than 200 billion square meters. So that is 2,000 billion square feet in that same period, right? And so we can maybe talk about in certain contexts that we can no longer construct, but this is not relevant for the rest of the world. So let's hopefully and please not do it like this, right? So let's go back to these structures and let's take one of those. So just to clarify to you what the impact could be of reintroducing these simple principles in everyday construction. So what I'm going to do with you is take a simple building, a simple floor plate here as a reference, 25 stories with 7.5 meter spans here. And we will introduce the principle that I talked about to replace all your typical reinforced concrete floor plates. So we will be, of course, taking advantage of the fact that more than 40% of the weight is in the floors, and we will count on those savings. You see that we are no longer at 70-90, because in a real building, it's not just about structures, it's also about acoustics, vibration, fire safety, and so on. So you have to put a little bit more material in there. So what happens? What are the savings by just replacing the floors by this principle? You would save more than 7,500 cubic meters of concrete for this one building. If that doesn't mean anything to you, I translated this for you. This is more than 1,200 concrete trucks that would not have to go to this one building site. And per story, so per level, you would save about 20 kilometers of reinforcement steel. So that is more about 16 miles of reinforcement per story, which is a lot of reinforcement altogether. And coincidentally, it nicely rolls out from Zurich, where I happily live and work, to Brussels, where I'm proudly from. So that is more than 600 kilometers of reinforcement steel. So in the beginning, I said it's not just about the material. Here, I should also not get carried away by just being proud of these volumes. What really matters is, again, the equation. So it's balancing the two. So what have I been saying here? So structural geometry, I think this is clear to you. We can directly reduce the material quantities. We can use state-of-the-art materials. So for example, the low-carbon concretes that are already commercially available today. But structural geometry, remember, also gives you another benefit. It actually allows you to reduce the stresses in the system. So you can actually use lower strength materials. And let's see how that plays out if you do a few numbers here. So structural geometry, again, gives you two things. Directly less mass, but also lower stresses. And so sorry, I don't know what the equivalents are in the US, but C30 concrete is a very standard, almost very regular concrete. So you see that the mass we can directly take off, but by going to lower strength concrete, so from a C30 to a C16, so C16 is typically not used for structural applications, you have an additional 20%. And then the state-of-the-art today of concretes that use clinker replacements in their cements. So for example, a CEM3 concrete, you can, on the material level, reduce the emissions by another 2/3. So even though we take only 60% of material out, you see that the total effect is 90% reduction in global warming potential. We will take the steel as is. So this is what we can do today, right? And so again, this is not an exaggeration. This is just, again, following the steps very clearly. So instead of forcing a material in a geometry it doesn't want to be, we reintroduce the natural form, and we have today a solution to replace all our floors with a system that has a reduction of a whopping 85% reduction of global warming potential. So let's look at the numbers a bit more carefully. So if we were to build, as we always do, right, our typical reinforced concrete floor plates, then we can do, the best we can do is 50% reduction of global warming. Where does that come from? We're playing on the concrete, but we have the same amount of concrete, but we have the same amount of steel. So that ends up being a reduction of half. Not bad, of course, but we have the same mass. So the numbers on the right, you see that we have a much larger kind of reduction, but we also save on the weight. What am I showing here? If you were to use regular concrete, so CEM1, OPC cement, so ordinary Portland cement-based concrete, which I think is criminal if you still do this today, by the way. So if you don't use any green concrete, then you see that we still have a reduction of 80%, right? So this shows you a little bit how important design is in doing things better, because everyone is talking about materials, and see now here how much design can have an influence. Another aspect that is important to point out is here this weight reduction, because this is direct dollars. Bill Gates has introduced the term of green premium. What does that mean? That sustainability, he says, is always, sustainable solutions will always be more expensive than our status quo, things that we have been optimizing for decades. Yeah, that is typically true, but so how can we then deal with this green premium? This is the strategy that we use. Because our floor plates are so much lighter than the reference, we can save on the columns and, more importantly, on the foundations. And so that means that on the scale of a building, and this building actually doesn't need to be that big, you can just already from 5 floors, you see this effect happen already. You can actually offer all of this sustainability at this cost neutral for the client. And I wanted to bring this in because at the end of the day, we can preach about sustainability as much as we want. If you want to have impact in real life, the cost is the only thing that matters, sadly. All right, let's now bring it all together with circular construction. So here I will first do a quick tangent and show you a project where we made another statement at the Biennale. This is a fully unreinforced concrete 3D printed bridge. How does it work? So we used same inspiration. We look at concrete as an artificial stone. So we look at stone in 2 ways. Global discretization, like an old aqueduct or a little structure here. But also on the level of the material, we wanted to basically have a perfect alignment orthogonal to the dominant force flow, right? So we use masonry on 2 levels. The global discretization of the bridge follows masonry principles. And then on the level of every single element, we try to align our material to be as perfectly orthogonal to the dominant force flow as possible. So this is possible because of 2 components, state-of-the-art 3D printing. You see that you can have these non-parallel kind of print layers and so on. And that allows you to place material only where needed. So we want, for example, structural depth, but we don't want a full solid section. So we make a hollow section. And on the right, you see exactly where needed. These are these bifurcating elements, and we want to be aligned to the force flow. This small bridge that I showed you, so 17-meter span, 53 blocks, all of these pieces were 3D printed in a total of 84 hours, right? And so this is exciting. It's something to kind of look out for. So here then you see my team together with our usual suspect, Theo Burgin, assemble this structure like a masonry system, dry assembled, again, to make sure that no one is confused about how this bridge works. And then here we basically put these pieces dry assembled together. You see maybe the black interfaces is neoprene, which is equivalent to you need something to distribute the stresses at the interfaces, and so this is a dry, disassemblable kind of joint material that we developed for this. So I was excited. This was a beautiful collaboration with Zahadit architects, with the code groups, a computational design group, and incremental 3D. I was excited that we could show this project, not only celebrate its aesthetic, but also to really show that we hit several of these R's. So we reduce by placing material indeed exactly and only where needed. We think of repair, and in fact that was already relevant because one of the pieces broke in transport and we could locally repair it. We keep materials separated, so the tension ties are separated from the unreinforced structure so that we have an easy recycling opportunity. And also, maybe not that relevant for this bridge, but you put it together like a masonry system and you can take it apart as easily as it was assembled. So you could literally reuse these components in another project. So this is how it looked. This was in 2021. You see some features, again, that were accidents in the fabrication that we then started to use to celebrate and show how this structure works. And so here we brought all these different ideas together to make a statement. Those of you who know about concrete 3D printing, this was, again, a provocation. We wanted to show that perhaps if you listen to this material, perhaps this is how you want to use it instead of trying to print full houses and causing a full mess that you have no idea how to maintain, how to upgrade, how to recycle at the end of lifetime and so on. So this was a bit of a statement this direction. But for me, the key point here is, again, circular construction made possible because of masonry on different levels. So this is the next step for me. It's not just about strength through geometry, but it's also about pure masonry systems that give you all of this circularity. I show you this just as one of these after-the-fact computational pipelines. I show this because this project, the entire team, all the way from designers, engineers to fabricators, never met a single time because the project was done 100% during COVID, and we only met at the opening of the bridge. And so this is again where computation, where Compass brought all of us together to make, to build on each other's strength and specialties. Sorry. We had an opportunity. The sponsor of this project was Holcim. Maybe there is, because there is a nice connection there. We had an opportunity to actually do a second iteration because this was for an exhibition, so it was only there for a couple of months. So this is Phoenix. So Phoenix, it's called Phoenix because it was built from the ashes of striatus. We took it apart, we grinded it, and this bridge was built entirely out of recycled striatus. So what's also special about this project is that this is now a permanent structure. So we used a totally new 3D printed material. This was built in Lyon in France. If you know France, it's a very bureaucratic process to get anything built. So I'm very proud that we have a permanent structure, a 3D printed structure using a 100% recycled kind of binder. So what we also did is that you could have criticized me, like, yes, but you make this efficient structure and then you build it with all this timber. So here we developed, again, a kit of parts using rented components and only very locally the use of timber. That allowed us to then pre-assemble things, assemble it really quickly, and really also to go one step towards a possible kind of commercial relevance of these projects. This is during construction, and there it is. So Phoenix came together. It's good that it's standing close to Holcim. They're measuring it all the time because we have been pushing quite a few things in this project. And again, cool to see it appear on Google Maps already. Nothing comes for free. So how did we learn from striatus? We reduced the block sizes so that we don't have these extreme angles. Why is that important? Because then we can use a lower strength concrete, a real concrete and not a cement paste. So we had to kind of restrain all the degrees of freedom here. We optimized the internal kind of stiffening schemes. But also, and I'm pretty excited that I always teach this beautiful Padre Pio church by Renzo Piano. I don't know if you know this project, but super elegant how basically the roof is being held by these arches. So finally, in a very humble kind of way, we managed to have the balustrade not connected at all, but just held in place by the arch action itself. Again, this was an important detail because that meant that the entire structure can be taken apart very simply, and that circularity directly was taken as an important design driver. This is part of striatus shredded, so it becomes basically the material for the next project. Okay, this is maybe a bit too much, so some numbers. And we see that we're doing better, but all right. Let's go back to this project. What I didn't say there, and remember, we are in the part circular construction. What I didn't tell you earlier, when we had our 3 centimeters of beautiful shell and so on, is that we built it like this. On a one-off mold, super expensive, super wasteful. Then we left the counter mold in it as well. We used polyurethane, big no-go, and so on. I hope you forgive me that we were already trying to push quite a few things in a real project, 3 centimeters, unreinforced, and so on. But this is clearly not a scalable way. This is not a sustainable way forward. So that meant that we basically addressed everything on top, but we didn't address the service life and the circular construction on the bottom here. So that meant that we evolved our system. So we took this first success, this first benchmark, to go to what we now call the Ripman floor system. So here I will combine everything that I've talked about. So we use our low strength, low carbon concrete. We keep our material fully separated so that we can easily recycle it, that a fully unreinforced structure gives you also all kinds of durability issues. You don't have embedded reinforcements that you have to protect that could corrode over time. You can have, for the material scientists under you, you can have carbonation happen the entire lifetime. That means that you absorb CO2 that typically you cannot do because that causes corrosion to the reinforcement. So here we can happily have this happen. We do dry assembly, like the masonry system. Again, this gives us an opportunity to take the structure apart and reuse the components directly. And then last but not least, we add prefabrication, so off-site, very precise construction, so that we don't have all these crazy safety factors that we need on site, because concrete on site is a messy business, right? So it also looks good. So we thought, like, okay, we had the success of the high-low unit, and there was quite a bit of interest. And that is why we actually were happily forced to start a spin-off appropriately called Vaulted. And the reason that we set up this spin-off in early 2023 is because we actually already won a competition with the famous Mike Gouyer from Gigon Gouyer Architects, an entire building designed entirely around the Ripman floor system. So this is, in Switzerland, by the way, a tower is anything above 35 meters. That's really not a tower. So this is a tower. It's called Crea Tower. It's a 10-story office building. What I'm showing you now is basically not a prototype, but a full-scale mock-up for the construction. So this project goes on site in early spring. And this was a test run with all the contractors to reassemble our system. So these elements are, again, low-strength concrete, C16, fully unreinforced, and dry assembled on site. So per bay, here moderate spans of only 6.5 meters, but this is assembled in 1.5 to 2 hours, and then you can move to the next bay and so on. So all of these elements were designed, engineered, and fabricated by Vaulted indeed. We develop also all the aspects, how to assemble it on site, how to lift the elements, and so on. This is, by the way, my partner in crime, Tom here, who was guiding the entire process and educating basically the builder that anyone who can operate a crane can install these beautiful masonry projects indeed. Here's some more images, and this is how it looks from the top. You see the reference is not far away. From the bottom, for this specific project, it looks like this. So now you could say, like, but are you sure? What about seismic? What about acoustics? What about vibrations? Obviously, this is a real project, so we had to test all of this. Here a nice ghetto load test situation with these little baths, the very efficient way to apply all kinds of loading cases. We did fire tests on the materials, but we had to do quite some advanced modeling. 5 different engineering teams have checked our fire safety models, and so no stone was left unturned in this project. We had to really carefully optimize the acoustics, not the room acoustics, but actually the contact noises, right? So this is a lightweight shell, so how can you make sure that you don't hear your neighbors and so on and so on? This was an interesting challenge. Room acoustics also needs to be checked indeed. And then this is, from all these tests that we did on the prototype, this is the final status quo. We hope to still squeeze it out a little bit. We reached not 85% in our very first project, but only 50% for now. But I'm very proud that we are doing this, and this is being done. So more than 6,500 square meters of RFS will be built in this project. It will look like this. From the bottom, it looks like this. And here again, a section. As you can see, all these little vaults appear. So this was done. This will be quite a large project. More than 150 bays, 180 bays of RFS will be installed. We have not sat still after this because we want to have impact and we need to solve it all. So we did full proper certification tests in Switzerland. So we have all the acoustical measurements, all the fire safety has been now tested in the national laboratory at EMPA so that we can go forward. All right. Well, maybe I will show this. So also here, we as Vaulted interact with all kinds of different people in the industry. And what is the solution? Compass. So we use 100% the open source framework to basically connect us to all the different players in the industry. And that is because all these different collaborators need different models, different information, and so on. But why I show you quickly this slide is not to say not to show you how we do it internally, but that all these different steps are basically based on open source packages that you can find on Compass. And I find this extremely important that we don't all keep all knowledge in all these bubbles. It's crazy how many people are reinventing the wheel by not sharing. And so we want to, even in a commercial setting, we want to lead by example and basically share open source, all the different packages that we developed to get there. All the way to, for example, advanced BIM modules that allow us to collaborate with industry. All right, and then in closing, and I'm going a little bit long, but I wanted to also address one more leap, right? Is that I'm excited to have impact in my context, but the reality is that most of this building is not happening in Switzerland. It's also not going to happen here. It's happening in the developing part of our world. And you see this in these clear graphs. You see us rather status quo up there. There will be a little bit construction in our context, but where it's really relevant is of course in Asia, and then increasingly the African continent. And in that context, I'm very proud that I get to work with the government in South Africa to address that aspect and to bring a version of what I've been talking about together with my local partners to that context. So more specifically, we had been working with the Department of Environmental Affairs from 2018 onwards, and they have this amazing concrete. I don't understand why not more people know about this. So what is this concrete? They have a big issue with non-indigenous plants. They were brought in colonial kind of context. These plants are not tailored for the African context. So they suck too much water out of the ground. They cause the local flora to disappear, also the local fauna to disappear. So they are massively cutting all of these non-invasive plants, these invasive plants. They're shredding them, and they found basically a bioconcrete where all this shredded bio-waste is being used as replacement for the aggregates and in this lightweight insulating concrete. This concrete has a super interesting behavior. So the first layer kind of chars. This is after a fire test. and then it is stable and it really works quite well afterwards. But they were using this concrete only for non-structural reasons, right? And then they got in touch with me because they learned, like, we hear that you can actually activate low-strength materials. You can take the steel out, which is really the bottleneck there for low-cost housing. That is the most expensive one. And yeah, they also are stuck with trying to build like we have done in wasteful ways, trying to address it a little bit. This is a picture that I took myself when I did some work in Ethiopia in the very early days. So what can we do there? How can we do even better? How can we take the steel out? Well, again, no surprise, it's by going back even further. What if we reintroduce the buttresses so that we can find ways for our load paths to go to the supports? And so we developed with them this kind of system to really have unreinforced buttresses, simple vaults, and then just one transfer beam that activates all of these elements. So we did these prototypes, big success, everyone was happy. You see these stiffeners appear again, right? So very much inspired by the early projects, John's work in Mapungubwe and so on. And then here, all of that great. We were ready to go to do a demonstrator project. What happened? Can you guess? 2020, COVID. South Africa was extremely badly hit, and so everything fell flat. But we kept thinking, and now we're back on track. So the project is back. We got some new funding, and we introduced one more idea to introduce the 3-hinged arch and to introduce prefab as well in this context. So here are some images. Actually, this is significantly less smooth than what I said before, because I have absolutely never shown this to anyone. This is hot off the press. This is we did this just a couple of weeks ago. So here what you see is that we use high strength material, higher strength material where the forces really want to be. We use lower strength material where we want to get to the floor level, distribute the stresses. Again, nothing new there, right? My title was Learning from the Past. Well, the Grostevinos already had this insight, right? If you want to stiffen your shells, you add either stiffeners or you actually raise it with a stabilized fill so that you have a solid package where you can imagine all these load paths to go. What we decided to do with our partners in South Africa was to use both, to have additional kind of redundancy to the system. And then, of course, the funding round that we are doing now is actually, we are certifying these floors. So we already have certified the material. So it's a fully certified material in South Africa that is called an agrément in South Africa. Here you see the load test, a lot of excitement. You see there in the back, Andrea joining, my research assistant, joining remotely and checking and instructing everyone to do it properly, all the different loading cases and so on. And of course, after you do the proper loading test, like anyone doing a structural test, you try to load it with everything you find, and sadly nothing happened. So this was basically all the cement bags, everything that they could find in the shop, so more than 10 times what it should be carrying. And then the only way to make this structure collapse is, can you guess, John?
Move the support.
That's right, take the tension tie out, and so then it's just a curved beam. That doesn't work, you need an arch. So if you take the tension tie out, this will come down indeed. So now the final step of this, so we are one step away from having full certification for not only the material but the entire system, is the full-scale fire test. But I wanted to show you a few more videos here to see what kind of unique, very weird rheology here, so very sticky material. But our local partners, Noncrete, so Stephen Lamb was in my research group for a couple of years, and then went to South Africa. He is from South Africa to really do a spin-off from his early work with the Department of Environmental Affairs to now bring this onto the market, and this is what you're seeing here. You see the relation between the higher strength material and the stabilized fill in between. And this is the last step. It's a full-scale fire test. So this is going to be exciting. In a couple of weeks, we do the full-scale test. And then maybe we can realize the vision of Noncrete to have a fully circular kind of building process all the way from dealing with these invasive plants, shredding them to really make a construction system based on that, to realize low-cost, dignified housing, as they call it there. And I will leave this as a teaser. This was the co-design workshop with the local community for the first demonstrator project that we will do there together. Then in closing, I want to bring it all together by proudly sharing this latest work by one of my star PhD students, Lotte. And she not only addresses efficient shells, but actually also how to realize the formwork. So she developed this very low-tech, robust formwork system based on folded plates that kind of come together like an accordion. It's a little bit more complicated. It's called curved crease unfolding. There's some interesting mathematical research that is at the base of this, but for me what is most relevant is that this beautiful equations then translate into a super efficient system. And so everyone in my team needs to find a way to somehow try to have impact. Maybe you recognize Lotte's little helper. He's sitting there in the room, right? He's now very excitingly studying here at ETH. But the key thing that I wanted to show, and Lotte feels very strongly about emphasizing, for example, that the entire project was realized when she was 7 months pregnant, right? And so she said, if I can do that in that stage of my pregnancy, so between 7 and 8 months, it was finished all the way until 8 months pregnancy, then I have proven that this is a very robust system indeed. So here you see this very simple sheet. You saw it being sewn together, very simple materials. You can then cast on site. Again, we are in our super sophisticated lab, so you could be maybe a little bit critical. Is this really scalable? So you will see where this formwork will go next. And then you take it apart and you can reuse it again. Super, super robust, easy to use. Beautiful use, again, of strength through geometry, both for the formwork and the resulting structure. Again, I have never presented this. Lotte does this part much, much better because it's her work, of course. And there it was indeed realized 1 month before Heidi. So beautiful result indeed. So what happened? We thought, okay, the proof is in the pudding and eating it. So let's ship this formwork to our friends in South Africa and see if we can just with minimal instructions, I mean, Mark being the minimal instructions, reassemble it and do it with their material there. So here you see indeed our friends, our colleagues, our collaborators casting a shell with their bio-concrete, which they call non-crete. This was a crew, and this was the result. So you see exactly the same. So the formwork traveled in two surf bags. And what's beautiful about this material is also this texture, these things that come through. And so here then at the end, you see the surf bags here on the ground, you see enthusiastic Mark. And so the surf bags are back to us, and let's see where this formwork is going next. Okay, so in closing, I talked about the impact we can have, right? Looking at this image and now realizing, I don't know if you knew this, I didn't know this, that 40% of the weight, so a lot of carbon is in the floors there. So that is this stupid element there. Oh, sorry. This banal structural element that we all need. We really can make a difference by solving this, and the beauty might be in shells. We need to share. So I didn't talk too much about this, but I feel strongly about us working on this together. So can we share more actively? That's why we do Compass. But at the end, in summary, I talked about structural geometry to reduce the mass. I talked about the right geometry. I look at stone, artificial stone, concrete, and that allows you to reduce the stresses and the carbon footprint. I gave you some hints how digital fabrication can help us realize these non-standard geometries efficiently without a lot of waste. I emphasized through the bridge, for example, the link between discrete masonry and all kinds of circularity opportunities, from reducing to recycling all the way to pure reusing of components, right? And then at the end, I just added it for completeness. That is kind of hidden a little bit in how we approach things through Compass. You have to find ways to bring all of this knowledge together. There's otherwise no chance to introduce an innovation in a real project. And so we have to really have an integrated approach. I believe this approach can be computational. And that is important because we have to address economy and productivity. Otherwise, we will have absolutely no impact. So here as last image, this was a snapshot in 2018 of our research group. The reason that I show you this image and I end with this image is because the cheerful colleague there in the middle with the glasses is Matthias Ripman. He was the third partner in crime next to Tom and me, and sadly he passed away in 2019, and that is why we call the system after his name. Very convenient that Rippen in German means ribs, and so in that sense it's also nicely aligned, but we do it in his honor, and we owe him also a lot. I wanted to end with that, and thank you for your attention.
Thank you, Philippe, for a very invigorating and inspiring and provocative lecture.
Thanks.
We have time for a few questions from the audience.
I went a bit long. So.
No, no worries at all. Would anyone like to go first? Yes, please. Come up to the microphone, please. And if anyone else has a question, just line up at either microphone.
Hi. Great presentation. I loved it. But I was just curious, if we were to use this kind of construction to address building for a larger population, how long do you think it would take to build like a very, very tall apartment building, like just in time-wise?
Yeah, I gave a little bit of a hint by saying that per floor area, we do it in 1.5 to 2 hours. So it goes fast. It depends kind of, right? Because what I showed you in a Swiss context is really focusing on design for manufacturing automation, even design for disassembly kind of paradigm, where we try to speed up things because of prefab. What I showed you in South Africa there, it's a more complicated story. We use combined prefab with on-site labor, because that's an important kind of aspect to be able to control things precisely where it matters, but also not take labor opportunities away, right? And so those will, of course, be slower because we actually want to engage people on site. So, I mean, I can't say exactly how, but yeah, fast, right? It's just in a couple of hours you have a bay and you just keep going up. Yeah, I hope that answers.
Maybe I can ask another question. I think you made the case really beautifully for the power of geometry and sort of intelligent distribution of material as one of the key levers in carbon mitigation in the built environment, and yet in the US, so much of the conversation is dominated by materials. And even in your first plot where you said, don't worry about operational, we're going to decarbonize the grid, no problem. That's what they're saying here now about materials too. Don't worry about materials. We'll decarbonize steel, we'll decarbonize concrete by electrifying at the source of the production. What is your sort of approach to communicating this alternative, sort of much more achievable approach that you're promoting?
Yeah, thanks for the question. Well, one of the things that you as professor, I find it actually rewarding to demonstrate based on numbers. Now they were very top level numbers, right? But to really take that material that everyone considers automatically as a problem, to actually demonstrate that you achieve kind of carbon emission kind of components that cannot even be achieved with timber construction. And so I think that's kind of part of it, to make people really open their eyes and make them reflect and see that even with such materials you can have that kind of impact. Sorry, I forgot there were much more nuances to your question, and I guess I'm nervous.
That's great. Yeah, I'm curious if in Europe and in Switzerland you have a sort of similar kind of debate in terms of like energy policy and decarbonization policy, where I feel like these design levers are overlooked, let's say, in policy discussions here.
Well, for sure in the past, I mean, there is a recent, and in fact, and this insight I have from the last New York Climate Week, is that in US there is now an important shift to acknowledge that it's not just operational and that the embodied emissions kind of really matter a lot. I think we're a little bit lucky in Europe that we have now also regulatory frameworks like the EU Green Deal. After 25 years of negotiations, is now being translated into really regulation, because you need incentives, you need ways to kind of introduce these kind of things. But you also mentioned about, I mean, don't worry about the material. It depends on what time scale, right? What I find exciting is that, again, and maybe I'm saying too much about concrete, but I like working in concrete because it is a local material. It is readily available all over the world, and it's an industry that is being scrutinized so much, has been scrutinized so much, that they have all the data from the past and they have a very clear decarbonization. So if I say today that we can already reduce by 85% the global warming potential of that floor element itself, right? Then in 5 years from now, it will be, I mean, we will be at 90% or even better. So we are dealing with a material that will get better. But the thing though is that we still have to use less, because if the industry says like we are going to compensate everything with carbon capture, for example, what do we do with all this carbon capture? It's also super expensive, this carbon captured. We also have a resource question. So now at least people are starting to count embodied emissions. I try to argue that this bean counting today is doing a little bit less bad today, but not thinking of end of life. That's why I try to make a case for circular construction as the next thing. And in fact, part of that is also being responsible to resources, and that is also not being talked about sufficiently, right? And you can't have it all. I think it's already good that it's increasingly on the agenda. It's good to see, and I mean, good luck for the world, depending on the election next week. So let's see if this continues. But because the big difference is that now we have federal standards that are requiring low carbon on the embodied emissions kind of attitudes. We have the big techs that, because of their ESG requirements for all their data centers, are starting to require. So there's a good trend happening. But yeah, let's hope that we don't go backwards. Yeah.
Thank you. Any other? Oh yeah, please.
Hi. I found the presentation super fascinating, and I was especially interested in the part where you were using the discretized materials and like using them just geometry and like just gravity holding everything together. Mm-hmm. You had mentioned that you were aligning materials where the forces wanted to go, and I was wondering, under different loading cases, mm-hmm. when there's like different critical loading paths, how do you kind of consider all of those?
Yeah. So the reason, I mean, so that's a more detailed question, but I'm happy to answer it. So you have a dominant loading case in these kind of structures. Even though we reduce the weight all the time, they're still comparatively heavy. And so that means that the self-weight is quite an important, so the self-weight of the structure plus the dead load, the finishes of, is quite an important kind of loading case. And so if you can already align to that loading case that is always there, that's a good starting point. Because of that ratio or that relationship between the self-weight and the live loads being not that much, the variations of your force flow are going to be controlled and are, so it is a good idea to already take that design load as a starting point and then to check if for the other loading cases it also works. That's kind of the idea behind it, right? Yeah. But thanks for the question.
Yeah.
Hi, Professor Philippe.
Okay, and then you, and then okay. Yeah, great. Go ahead.
Did I
please.
steal anyone's opportunity?
No. Go ahead.
Yeah, I watched your presentation last year in ETH mentoring. So 1 year passed. It's great to see how you pushed it forward. I have more and more application.
Which presentation did you see?
What?
Which presentation?
ETH mentoring in New York last year.
Okay,
Sorry,
yeah.
AEC Tech.
AEC Tech, yeah, okay,
Yes.
cool. Yeah.
So I'm a professional working in Boston, structural engineer. So for this kind of concrete floor, if we choose the prefabricated option, we usually use hollow plank.
Yeah.
This hollow plank can span 30 feet or roughly 10 meter, 10 inch or 25 centimeter, like 8 times thicker than what you designed, right?
Yeah.
And we have supplier usually select like BPDL, and we talk to them, and this kind of hollow plank is like in massive production, easy for us to select.
Yeah.
I'm wondering, like for the vaulted floor, and you guys make a lot of effort to push it into application. Did you guys have any discussion with the US supplier?
No.
And if so, did they mention any challenge to implement that in US market?
So first I want to address, yes, there's many, so holodeck is one, but actually already kind of hollow core. I don't know if you know these planks, they span in one way. They're super optimized. If you look at these carefully, there's almost no steel in them. It's absolutely spectacular how efficient they are. What is a big difference with all these systems is that you still have embedded reinforcement, you still are activating bending, so you design for peak stresses. You cannot do the holodeck, you cannot do the hollow core with low strength concrete, and it starts to matter because they reduce less steel, less cement. But the key thing is they're not circular, right? So either you take them out entirely, with hollow core you could, with a holodeck not, you cast them and so on. And so the thing is that for me that is the next step. Yes, if we do our today bean counting, our embodied carbon and we calculate it, yes, then we can have almost the equivalent systems. Still compared to the system that you talk about, we will be half roughly, right? Or 1/3 for sure, but in many cases we will be half of the embodied emissions. But what you don't have is circularity. And so I have to hold on to that because I care about the end of life, and so I want easy recycling, I want reuse of components and so on. About the US market, no. The thing is that there is, not yet, the thing is that there is, I share this very proudly and as a nice success story, but this is also 15 years of stubbornness, of a lot of funding, of not giving up, of fighting all the skeptics that say that all of this doesn't make sense, that all of this, what about redundancy, what about plasticity, ductile behavior, what about and so on. Of course, we had to demonstrate all of these things, and it's all in the system. So why I'm saying all of this is that we have to now do a few projects really well in a context that we know well, where ETH is the MIT of Europe, so it has a lot of, or the other way around, who knows. And so it has a big reputation, we have the right partners to work and so on, and we need to do it right? And so this needs to really be done properly. And then indeed, the US might be the next market. In fact, I might start in Texas. Can you guess why?
I don't know.
Two things actually. So in Texas, like in Switzerland, the engineer that signs off, that's all you need, right? So great, that's a perfect context to go forward. You don't have like a city engineer checking all your stuff, right? So you don't have this. And secondly, no earthquakes, right? So I'm happy to start in a context where we don't have all this complexity coming. That's something that I didn't explicitly say. What I showed you in the extreme versions that I show you today, please don't build like this in Turkey, in the West Coast, in Tokyo, right? Not ready today. Not fundamentally an issue, but you might have to add a little bit of fiber again to make it safe. Yeah.
Thank you. Looking forward to your sharing next year for the project in Texas.
Maybe in Texas,
and
yes.
I'm looking forward to use the Rhino Vault in one of my project.
Thanks.
All right, the next question,
I guess simple question, but how do you think we became so inefficient with materials?
Yeah, there's many reasons. I think a key one is this shift between the cost of materials versus the cost of labor, right? I think that the other side effects are modernism, where, for example, a straight line was preferred, right? Maison Domino and so on, that as reference, that was kind of that started an entire generation of architectural design and so on. But I think the key one is this relation between cost of materials and cost of labor. And so indeed, it is super simple to make a straight formwork, to just put your materials that are not expensive comparatively, and then just cast, very simple. And we have indeed optimized these kind of construction techniques because it's so labor efficient, right? And so for me, the only way forward is sadly indeed through incentives, is that we start to pay the real cost of materials. And so the real cost of materials needs to include the cost to society of materials. And so one example is indeed a cost for carbon. So in this cost, you could actually then take in the cost for healthcare, the cost for all the results of pollution, of basically climate change and so on. And so I think we are at that point, at least in Europe, we're at that point that we are starting to be able to charge the real cost to materials considering embodied emissions. Yeah.
Thank you.
Thanks for your question.
Maybe I'll ask one last question, Philippe. It's very inspiring to have you here, especially as an alum of multiple graduate programs here at MIT, and I know you met with some of the graduate students yesterday, but and I knew you when you were a graduate student and I was an undergraduate. It's amazing to see how far you've come. You were already brilliant as a early teaching assistant, but reflecting on your trajectory so far, like what advice would you give to students who are looking to follow in your footsteps or to like take these ideas out into the world?
Okay. I think one thing, and this is more a challenge in my context, in a Swiss context, in a European context than here in the US, is that I think you have to educate yourself. And so one thing is in the sustainability, but where I want to go with this is that being just an architect in a more traditional kind of sense is, or Beaux-Arts or very old school kind of way of thinking is really not sufficient. So you want to be able to combine it with an additional kind of specialty that allows you to tackle some of these projects. So in my specific career, this is with structural design. You could say the same with materials. You could say the same with the operational emissions and things like that. So I think you're well set here because people come from all different interests and backgrounds, and you're entrepreneurial problem solvers, right? In how teaching and research is being done here at MIT. But for me, actually, the most important thing is just, don't take no for an answer. Challenge everything. I'll give you an example, if I may.
Yeah, please.
So when I talk to engineers, then they often directly dismiss our system because they say like, you don't have your diaphragm, for example. I'm like, yeah, okay, but diaphragm, what does that mean? It basically means that your horizontal forces need to be transferred horizontally and find their way to whatever bracing scheme you want to activate, being it a core or being it kind of a cross, a truss going up and so on in the facade. So that doesn't mean that you need a continuous layer of 10 to 12 centimeters of concrete that bring these forces to the support, right? And so that is an example, like instead of just saying like, in every project we need that. No, we don't need that. It's because we built our flat floors, we have our concrete anyway, so it's there, so we use it as a diaphragm. So you dare to question everything. What is diaphragm action? Why do you need it? Sorry, this is very specific, but I wanted to make it specific as an example of, you get this from engineers, you get this also in the building codes, right? So where do these codes come from? Like architects tell me, yeah, but these arches, you will have more your floor-to-floor height ceiling is more than when I use my very optimized thin floor plates. Yeah, maybe, but if we can integrate our building systems in these things, if we can start to if we only have at the columns a reduced floor height and everywhere else we have more height, is that maybe possible? And so the codes don't apply there, right? And so you have to continuously challenge everything. And so, it's appropriate that I'm Belgian because we are experts in bending rules, breaking rules, ignoring rules, and so on. So I think you need a little bit of Belgian in you to get ahead in life. No, so anyway, sorry. No, well, challenge everything and don't give up because it's hard. There's more naysayers than people that want to support you. Yeah.
Excellent advice, Philippe. Please join me once more in thanking Philippe Block.
Thank you.
And one final announcement, the lecture next week on Thursday, November 7th is a screening of We Start With the Things We Find, the Lot Tech film by Thomas Piper. Please join us for that. Thank you.